So for question 5, we have something that tests your concepts on continuous annuity. So we have an annuity that pays 1 minus kt at time t. So if we're at time 0.5, you can imagine at that very moment we're receiving a payment of 1 minus k over 2 per annum. And then this expression, the present value of this payment scheme is equal to f minus g minus h. F is the present value of a perpetuity of 1, so it pays 1 continuously forever. G is the present value of an n-year deferred perpetuity. So this is a perpetuity that pays 1 minus kn, so this is a constant. So it pays 1 minus kn per annum forever, and then it's n-year deferred, so it starts at time n. And then based on all this information, we need to find h. So first of all, let's try to find what f and g should be. So recall f is an annuity that goes on to infinity, and it's continuous. And then in order to find this expression, this is just substituting infinity into this expression. And then recall this is just equal to this. You can derive this using integration. And then substituting infinity, that's just equal to 1 over delta. So that's going to be f. See, second expression, g. So g is a present value that's n-year deferred, and the payment is 1 minus kn per annum. So essentially, if we have something like this, so we have a 1 minus kn payment per annum. So you can view this as a payment of 1 per annum. This is a payment of 1 minus kn per annum. And then we call that it's n-year deferred. So we need to multiply this by v to the n to bring it back to time 0. So if you have a timeline, the payment starts here. So it's continuous at a level that is 1 minus kn. So this expression here gives you the present value at this point, and then to bring it back to time 0, we multiply by v to the n. So this is the expression for g. Now, in order to find h, we know that f minus g minus h is equal to this payment here, this payment of 1 minus kt per year, and it goes from 0 to n. So in order to find h, we need to find the present value of this payment scheme. So let's do just that. So the present value of that payment scheme is an integral from 0 to n, vt 1 minus kt dt. So you can break this up. You can think of this as the instantaneous payment at time t, and then we need to bring that instantaneous payment back to time 0, so multiply by v to the power of t, and then we integrate it to add up all the individual contributions. So in order to integrate this, let's try to break it up. So k is a constant, I'll pull it out. So now we need to do a bit of integration. So integrating an exponential term v to the power of t, that's equal to v to the power of t divided by natural log v, 0 to n. And here we need to do integration by parts. So we're going to keep this term and then integrate the v to the power of t term. So we get v to the t natural log v, 0 to n, and then minus. Now we're going to keep this term and then differentiate the t. So this is just standard procedure for integration by parts. So I'm going to substitute this in for now. So minus k, I'm going to substitute this in as well. N v to the power of n divided by natural log v. The 0 just becomes nothing because 0 times v to the power of 0, that's just 0. Then we're going to plus k, this integral, so I'm going to integrate it right now. And then there's going to be another natural log v at the bottom, so we get a square, and it goes from 0 to n. So continuing where we left off, so for convenience sake, I'm going to flip the signs. So originally it was v to the n minus 1, now it's 1 minus v to the n, and I could do that because natural log v is actually equal to negative delta. So recall the definition of delta is natural log 1 plus I, and because natural log v is just natural log 1 plus I negative 1, so natural log v is just the negative of delta, because for a logarithm I can pull this negative 1 over to the outside. So natural log v is equal to negative natural log 1 plus I, which is equal to negative delta. So just going to apply that. So I'm going to do the same thing for here. So instead of a minus, I get a plus. And then I'm going to change the natural log v to a delta. And then over here we get plus k v to the n minus 1. And again, I'm going to switch out the natural log v for a delta, but because there's a square, I can't flip the signs here. So we just get delta squared. And so there we have it. This is the present value of the payment that pays 1 minus kt at time t. And then we know that this is equal to f minus g minus h. So ran out of space, so let's just put this here. So we can just substitute f and g inside, and then with a bit of rearranging, we can find h. So recall what is f. F is just 1 over delta. So 1 over delta. And then g is just 1 minus kn divided by delta v to the power of n. And then h we don't know. Our goal is to find h. So this expression is equal to this. So both of these expressions should be equivalent. So with a bit of rearranging, we can find the expression for h. So 1 over delta, both of these can cancel each other out. We have a negative v to the n over delta, so we can get rid of these terms. They both cancel out. And then with this gone, I can just put the negative sign here. So we get a kn v to the power of n divided by delta. That's the same as this. We can take this out. And so after taking all these terms out, you see that negative h is equal to k times vn minus 1 delta squared. So h is equal to k times 1 minus vn divided by delta squared. So this is our answer.